Everyone, and welcome to this week's SQL Query training presented by Emergency Reporting. Get the screen sharing going here. This week we'll be covering the merge statement and recursive queries. The presenters will be myself and Aaron Buma, and we're with Emergency Reporting. For all those joining us remotely, for all of those who are joining us remotely, for any questions via Google on-air broadcast, we'll try and address most of those at the end of the training. But if there's something relevant, we may take it partway through the training. Keep in mind the training is provided by Emergency Reporting, so we're paid to make this training available for the team here, and we've decided to share it with the world. So emergencyreporting.com for more information. And slides and sample code are available for download at my website at stevestedman.com. I'd like to welcome some viewers. We've got 20 people who have RSVP'd that they'll be attending from the following locations that are listed on screen now: Bellingham, Riverview, Warren, Jacksonville, Chennai, Belarus, Trowbridge, Hyderabad, and Bucharest. So welcome everyone. So keep in mind, this is a live on-air broadcast. There may be a slight delay. Sometimes it's 40 to 50 seconds. Sometimes it's a little bit more than that from when we actually say or do something here until you see it on the other end. And we're still learning the process and working out the details here. So please be a little bit patient with us. And then afterwards, the sessions will be available on my YouTube channel about an hour after the presentation ends. So that's available at stevestedman.com/YouTube. And at the end, we'll take as many questions as we can, even if it runs over our 90-minute block a little bit. And if you want to open the Q&A window, if you're in the watching from the Google on-air broadcast, there's a link up in the top right corner that's a little 3x3 grid icon. You can click that and then select Q&A, and you can see what people are asking, or you can ask your own questions at that point. And just keep in mind, when you ask a question, it's a little bit delayed for us, so be patient there. Question that already came in earlier this morning from a viewer. He asked, on our webpage, you mentioned that training will be covered in 45 weeks. Do you mean to say that preparation for the 7461 exam will take almost a year? Well, that was the original plan. But as we've gone through this, we've been doubling up trainings, and we've been doing 2 trainings, one by Aaron and one by me, pretty much every week. And I don't think we're going to be able to do that with all the topics. But for many of them, we're going to do that, and I think that'll trim it down to about 30 weeks of total length in the program. Now, one of the things we're going to do occasionally, and we'll do this next week, will be a review session. So next week will be a review of everything we've covered up until this point, but still the whole thing I think is going to take around 30 weeks. And we'll see how it goes with everyone as we get into it, and we may adjust that as needed. So be quite a bit of training over most of the rest of the year, but not the entire year. So on to today's training. The things we're going to cover, Aaron's going to cover the merge statement, and that's one of those that really jumps out at me as one of the, I don't know, it's introduced, I mean, it hasn't been in SQL Server forever, but it's one of those that I had a bit of trouble with, I'll admit, when I took the 70.461 exam. So make sure you know that one. And then we'll take a look at data recursion and what some people consider recursion with a self-join, and then on to recursive CTEs. So at this point, I'd like to hand it over to Aaron.
The merge statement. So the merge statement is a handy way to do update, inserts, or deletes all in one statement instead of the traditional do an insert, check your row count to see if the row had already existed and you'd inserted 0 rows, and then do an update, or the reverse of that, of perform an update, check to see if any rows were affected, and then insert if no rows were affected. So it's hard to explain. So we're going to look at an example first. The example is combining like your baseball card book with a new deck that you just got. So you want to be insert the new cards from the deck into your baseball card books, the ones you don't have. And then if there are cards that you have already, in this new deck that you just got, you want to keep those, but you only want to keep them if the value, say, is greater than $5, if they're worth something still. So what you're going to want to do is kind of toss or get rid of the ones that you already have and the value isn't great enough to keep. Without using a merge statement, a pseudo merge statement, you'd insert the deck or the cards into your deck that you don't have already, and you'd say update the quantity of the cards in your deck that match the cards in the new deck if the value is a certain value. So that would be 2 or 3 SQL statements. But with the merge, you can do it all in one. So you'd be inserting into your deck when they match and the value is less than $5, then just toss it. Don't worry about it. When they're matched, so this would be all the cards in your deck that are greater than $5, matching the new cards, you'd want to keep those and double sleeve them. So you perform a logical step if they match, the value's high enough. And when they're not matched, you perform a different logical thing. You just keep them all, or keep the ones that you don't have already. So in a merge statement, you can perform 2 or 3 update, insert, or delete statements. I've heard the merge statement called the upsert, but that's kind of a misnomer because it can do more than that. You can update, you can insert, or delete all in the same time in one statement. If you have, you can have a matched, you can have a matched and a not matched. You could just have a not matched. You can have up to 3 statements in one merge, 3 conditions in one merge statement. There's this multiple condition statement here, this one for a matched and an additional condition on there. And what that does is it narrows down the rows that match on, say, X and Y, because only one operation can be done per row. And this first one here will reduce that result set. So if it happens to meet this one condition here, it won't show up in the second one. So you have the least results here, and then the rest of the matched ones in this matched. And then not matched is obviously, everything else. In the merge statement, you'll have a source table, which you're merging to. And then, or the destination table is where you're merging to. The source table can be a derived table, or a set of variables, similar to a row constructor. And you can also use the output clause to log changes. So whenever you do an insert or an update, you can get data out of it as well. And this was introduced in 2008. It also requires a semicolon at the end. A lot of statements in SQL do not require a semicolon. It's just clean code to have them. But the merge statement actually requires a semicolon, and you will get an error. It won't compile if you don't include a semicolon on there. So on to demo. First, we're going to drop and create our database just to make sure we know what we have. We'll create an inventory table that has the camping store items in it. Items, categories, description, quantities. We'll create a categories table. So first we will add a new item. We don't know if that item exists, so we will be doing the pre-2008 style of we'll do an update, and if we get 0 rows affected, that means it wasn't in there, and we will turn around and do an insert. We can see here that there was 2 statements ran. First one was 0 rows affected, and that was the update. And then the 1 row affected comes from the insert statement. And we can see now that we have the red hatchet in our inventory table. And we'll run it again. We can see 1 row is affected because it existed. It ran the, since it existed in the table, it ran this update statement. More than 1 row, more than 0 rows were affected, so it didn't do the insert. So we see 1 row affected from the update and 8 rows affected from the select star. You can see it's in the table still. You can insert multiple rows. Now we're going to run it with the merge statement. Let's just look at it first. So here's the destination table. This is the syntax. I added line breaks in here just to help show the different areas in the syntax. The merge table, so top merge our table, and I always put an alias on there just to help later on. And then we use our source fields, or source table in the using. So using select all our variables. This can be a derived table. It can be just a select query if you want to merge multiple rows. In this case, we're just merging 1 row into the inventory table. So it's just a select of all the variables. And you can alias that. And I alias its source. And then after that, you have in parentheses the names of all the columns. So you're kind of defining the output of the source table. For the next line, this is where you join the or your search condition, your merging search condition of the source table to the destination table. In this case, we are joining on item SKU, which is in this case AX13HT So when the system runs through the inventory table and compares it to the source table, for each row, it will look at the item SKU column. You can have multiple columns in this merge search condition, or just one. In this case, it's just one. And when those 2 columns match up, it will run this chunk here. Down below is the not matched. Earlier I mentioned you can have 3 in here, a matched and an additional condition. We'll cover that example later on. Right now I'm just covering a matched and not matched setup. So when the item SKU in the inventory table matches my variables, we will update the inventory table destination, aliased here, to whatever the matching item SKU has in our source table. If they do not match, so if it can't find it, it will insert similar to your regular insert statement. You say what destination columns you want. You don't have to alias these columns with destination. It already knows. And then you insert values, and the values we're going to insert are from the source table or derived table. And here's a little note that you have to have that semicolon on there. So we do not have a blue hatchet in our inventory table, so we should expect to see one row affected. See? One row affected, and there's our blue hatchet. So, and we can run it multiple times, and it now runs the update statement instead of the insert statement because it can find that item in the table.
Almost seems like more code to do that. That was functionally equivalent to the row count before, right?
Yes. So the question was, our comment was that it requires more code than the update and then check for row count and then insert. And yes, it is more lines of code, but it performs faster. It's only one statement instead of 2 or 3 or 4 statements, because you could check for the add at row count, or you could run a select on the table to see if that ID that you updated is in there, and if it's not, and then do an insert. So yes, there's more code, but it performs faster, and I'd say less prone to errors. Okay, so now we're going to just add the output clause. We're going to insert or update a orange hatchet, and what has changed is I added this output line at the end of it. And just like when you do an output on an update or a delete statement, you reference it as the inserted rows. You can also have deleted rows or hard-coded values in here. You can treat it just like your regular output clause. One thing to note is it comes after everything. You don't put it in between the insert and the values clauses like you would with the regular insert statement. And again, semicolon is required at the end. So now we're going to get 2 result sets back. We're going to get whatever was inserted or updated, and select star from the inventory table. So you can see here, this is the output record set here. Our orange hatchet. We can see it's now in the inventory table as well. We can run that as many times as we want. And it only, well, now that it's in there, it just updates the orange hatchet record over and over again and has the output records. You can use that for logging or change tracking or auditing, similar to how you would with the output clause. Now we're going to cover multiple match statements. So in this sample, kind of business problem we're going to try to solve is we're going to need to discount the items where the inventory on hand is less than 7. We want to discount those, lower the retail price by 10%, just to kind of get them out of the door. And if there's 0 on hand, then we want to delete them. So if you weren't using a merge statement, you would need to do that in multiple queries or multiple statements. And with the merge statement, we can do it all in one. So using merging to the inventory tables or destination table, instead of a hard-coded list of variables, we're going to have a little sub-select here, subquery, this select inventory ID and quantity on hand, where the quantity on hand is less than 7. So that'll give us a list of candidates that we want to work with. We're going to search or use it as a merge condition on the destination table, which is inventory, to our subquery on the inventory ID. So when it's matched, because it's always going to be matched. So when it's matched and the quantity on hand is 0, then delete from our destination table. So that would leave everything else in there that matched would have a quantity on hand less than 7 but greater than 0, or not equal to 0. We want to update those and set the unit retail price equal to itself times 90. So we're going to reduce it by 10%. And run that. And then this first result set is a select star before the merge statement. The second result set is a select star after the merge statement. We can see that this red sleeping bag has a quantity of 5 and unit retail of 19.99 in the first result set, and in the second result set, that same red sleeping bag has a unit retail of 17.99. And same with the black sleeping bag. The black sleeping bag down here. So that was the reduce the price by 10%. Well, what about the other matched? The orange hatchet that we inserted previously had a quantity on hand of 0, and it shows up in the first select star. And then after the merge statement, it no longer exists because it met the criteria of quantity on hand was less than 7, and it was also equal to 0. So it met this condition right here.
You can only have one, or you can only have 2 matched statements and 1 not matched statement.
So the question was, can you only have 2 matched statements and 1 matched, and 1 not matched statement? And yes, that's the maximum you can have. But you can have any combination of that. You could have 1 not matched, and that's it. Just disregard all the matches. You could have 1 matched. You can have 1 matched and 1 not matched in any order. But the only thing that you have to have when you do a matched or 2 matched statements, one of them has to have an additional condition on there, and it has to come before the general matched statement, because each row that you're doing the merge on can only be true in one of the matched or not matched clauses. So
it won't let you delete and update the same row
Yeah.
at the same time.
yeah, so if we pulled that one out and put it up here, then say in that orange hatchet case where the quantity on hand was 0, it would match, it would be true here, and they would perform an update, but then it would also be true here, and it would delete it. So that's, that doesn't work logically.
It doesn't work logically, but does it work? Is it all a syntax clause? Like syntactically, is it valid?
No, syntactically it's not valid.
Okay.
So you need to have your kind of fine-grained match statement first,
Yeah.
which will eliminate that smaller subset, and then your overall matched condition after that, which will get the rest. And then you can have your not matched down here, your when not matched. You could have your when not matched in the middle, or you could have your when not matched as the first condition.
Sounds like a good test switch.
So it's a very powerful tool to use, because you can take care of multiple updates or deletes, multiple logical paths in one statement, and you can put an output clause on there, which will further complicate things, but you can get a lot more done all in one statement and not have to run multiple queries at the same time. All right. Any questions before we move on to recursive queries? Okay.
Actually, I do have one. I've tried to use a merge statement on a table of trigger fails.
Triggers will occur after the merge statement is used.
But actually, the merge statement, it does indeed fail. It
Yeah.
tells you you can't use the merge statement when the table has a trigger on it. So that's one thing you need to keep in mind. And when we talk about how triggers are evil quite often, there's another good reason why we consider them evil.
All right, on to Steve and recursive queries.
All right, thanks, Aaron. So, some feedback that came in while Aaron was talking, one of the things that came up was using the go statement a little bit more in the query. So if we use the go statement, what it does is it breaks up the chunks of code, and some of the red squiggly lines you're seeing, like on variables being declared a second time in the same batch, would go away. So that's one of those things. Thanks, Mark. We'll focus on doing a little bit better job on that next time. All right, so jumping into recursive queries. Actually, it was just last week or the week before, we covered common table expressions. And when we got into common table expressions, we spent most of the time talking about how do you do common table expressions, and then we kind of jammed in at the very end of it, how to do recursion with common table expressions. So what we're going to do is look into a little bit more detail and some example code on common table expressions for doing recursion today, doing some fun stuff there. And then this is one that I don't entirely agree with, but in some of the books and documentation I've looked at, some people consider self-joins to be recursive. I don't really consider that recursion because it's not really calling itself, it's just joining the same table together. But we'll go over an example of that just to sort of review and see how it compares there. And then keep in mind with CTEs, it's considered recursive when the CTE references itself. And we'll take a look at some examples around that where we'll build out the anchor query and then multiple recursive queries that keep getting called or calling itself back. And then keep in mind that recursion stops when the recursion query produces no results, it's just out of things to return, or we hit the max recursion level, which we'll look at code examples of all of that. But here are some uses for recursion, and I think we touched a little bit on hierarchy when we looked at CTEs, like department hierarchy, and then I showed a royal family hierarchy that I just sort of showed it. We didn't really have a chance to explore how it was all built out. Today we're going to explore how that gets built. We're going to take a look at tree path, and what tree path is it's sort of a path through some tree structure. So if you're looking at the Windows file system and you're looking at C Windows /system32/driver/etc/hosts or something like that in a path name, the tree path can be built out with a recursive type query for those type of things where you can put in whatever divider you want along the way to build those paths out. We're going to take a look at some recursive calculations, some interesting mathematical sequences, string parsing, and actually doing a varchar diff function where you can pass in two strings and have it tell you what's different between the two. And then finding holes. And you might think, well, finding holes, what's that mean? Well, if I ask you to write a query that says select something out of a table, most people can do those queries. But if I ask you to write a query that says, show me what's not in that table. For instance, if I had, we'll look at an example of people's ages, and it's a group of people aged 1 to 50, and it's a random sampling of about 80 people. So you can imagine there's some people with duplicate ages, and there's some people with, or there's some ages that aren't represented. So show me all the ages that aren't represented in a group like that. Think of it if you were like a doctor and you had your calendar, or you were writing code for a doctor that had his calendar, because doctors wouldn't normally do this probably, and you're trying to look at what days in the calendar that doctor has no appointments, so they can go and schedule golf day or whatever it may be. It's real easy to query a table and say, give me all the dates that I have an appointment on, but to query and say, give me all the dates that I don't have an appointment on can be a bit trickier, and we'll take a look at some date calculation stuff around that you can do with recursive queries. I don't have a lot of slides today because it's all demo, so let's jump into the demo now. And I'm going to use the same query training database we've been using each time. I'm going to create it and drop it. drop it and create it so we start fresh. I'm then going to create a table called royalty that we took a look at before. And again, like we looked at in the past, this has the British royal family in it. The youngest one that we've got in here, we'll take a look, is Prince William right here. And then everyone else in the list is one of his ancestors, either on his mother's or father's side of the family. So we'll fill that table up with that information. We'll look at what's in the table. And hopefully if you were looking at the insert statements, you'll agree that, yeah, that looks about right. Everyone in the table has an ID. Everyone in the table has a name. And some of the people in the table have their mother and father listed, and others it's null, meaning we don't know who their mother and father was, or we just don't have that data. And so let's take a look at what some people consider a self-join as recursion. And I don't consider this recursive, but we'll go through it and take a look at it anyway. So here we take a look at ID of 3, which is George VI of Windsor, King of England. His mother is ID 2 and his father has ID of 1. So how do we go about getting the mother and the father's name displayed here? Well, one way to do it is to start with an inner join. And what we're going to do here, oops, hold on, is we take the table royalty, we're going to alias it with the alias of just R. So the R dot star that we're pulling up here is bringing back everything from the royalty table, which is what we just brought back where R ID equals 3, which is the first person we started with. We're then going to inner join back to royalty, and that's what makes it a self join when we're joining to the same table. And we're going to alias that as mother, meaning it's the mother's side of the family that we're going to join to. And on the original table's mother ID, or mother, which is an ID, linked to the mother table that we just aliased here, .id, and this should show the person with the ID of 3 and his mother. So let's take a look at that and run it. You can see here we get George, and his mother is Mary, Princess of Teck. Heck of a name. Don't have people named like that anymore, do we? So what if we now want to take a look at his father? Well, we do a similar thing. We go here, let's see, we take a look at this query. We have mother.name that we just asked for. Oops. We have the father's name, and then we do a second inner join to royalty as father on the father's ID joining up to the father's table ID. And what that will do is that will give us, when we run it, the mother's name and the father's name both for that person. Okay, well, not very interesting. You could have written 3 different queries and done that, but let's see where we can go with it next. So what I want to do on this to avoid confusion, because when we look at the results there, you can see that the names on all of them is just name, name, and name. And you don't know which one is the mother and which one is the father necessarily. I mean, you might guess Mary versus George, but you might not know based on some of the names. So what we're going to do is just add a couple of aliases in. And when we run this query, it's just a double self-join. They've been aliased with the mother's name, and I've thrown out the IDs that I don't really care about. So we've got the child, the mother, and the father listed. Okay, now that's a little bit more interesting. But what if we take that same query, I'm just going to skip the where on it. I'm going to drop the where off when I run it and run it again and take a look at what we get back looking at the entire table. Well, the entire table originally had 19 rows in it, but now when I say select this with the inner joins, we only get 9 rows back. And the reason for that is because some of the people, not everyone in the tree had parents. Some of those parents were null. So the inner join, when it's trying to join on the mother's ID or the father's ID, doesn't include those other columns because there's nothing that's matched there. So the way we can fix that is we can change those inner joins to be left joins, which effectively says, give me everything out of the initial royalty table, but if there's not a father or there's not a mother, show the row but represent everything else there with nulls. And then because of the nulls, we're going to wrap an is null around the mother's name and the father's name and replace them with an empty string, because an empty string is more appropriate in our example here than showing null. Nobody's actually named null, I hope. So we run this, you can see now we get the entire 19 rows returned, and those that actually have parents are shown, and we can build kind of a hierarchy out this way. So if you had whatever application programming language you're working in that was calling this query, and you needed to go now build some kind of visual representation, you could take this data, put it into some kind of structure you want to work with, and figure out how you're going to display that in your application. However, I still don't agree that that's considered recursion. So let's jump into recursion with common table expressions again. So we'll just take a look at the royalty table again, same 19 rows we've been looking at, nothing up my sleeve at this point. What I'm going to do is start with selecting star from royalty, where the ID equals 17. And if we look at who 17 is, that's Prince William. He's the youngest one in the entire family tree. And you can see his mother is ID of 16 and his father is ID of 15. Then what we're going to do, as we put that inside of a CTE called Royal Tree CTE, we use the union all. And if you remember from when we touched on this before, the union all is what makes this a recursive query. The union all is being joined up with something else that's going to reference the CTE itself. So let's zoom in on that a little bit. And here, the select statement in the bottom of it is we're going to say inner join back to the Royal Tree CTE, which is the CTE here, and that's where the code's going to call itself. We're going to alias that as RT for the Royal Tree versus just R for the royalty table here, and we're going to join it on the rt.mother equals r.id. So here we're saying give me Prince William, and then for everyone in the result set, join that person to their mother and return the row, the star, so the entire row for their mother. And then do it again and again and again until there's no more results returned. So it's going to return Prince William, his mother, his mother's mother, his mother's mother's mother, and so on in that direction. So if we highlight that and run it, well, we don't have, it doesn't go very far back on that side of the family. We have Prince William, his mother, Diana, and his mother's mother, Frances. Okay, well, that gets us partway there. We've got the maternal side of the family tree, sort of one branch going out there. Not even the whole tree, just the mother's mother side of it. Now, if we do the same thing with this query, and all we're going to do is just replace the father, where it used to refer to mother, refer to the father's side. When we run that chunk of code, we start with Prince William. We get his father, Charles, his grandfather, Philip, his great-grandfather, Andreas, and his great-great-grandfather, William. Okay, so what we've done now with these two different queries is one of them has started with Prince William, and then for everything in that result set, it looked up their mother and added that into the result set, and then everything new, it looked up their mother. And then this one did the same thing with the father. So we basically have a mother's line of mothers and a father's line of fathers going up either side of the family tree. Okay, it's a good start, but it's not really where we want to go if we want to really take a good look at a family tree. What we want to look at here, we're going to start out with the same Prince William at ID of 17. We're going to include everybody or all of the fathers of everybody in the result set, and we're going to include all of the mothers of everybody in the result set. Now, originally when we looked at this, it just went up the mother's line of mothers and the father's line of fathers. But in this case, it's going to, for everybody that's returned for every one of these, it's going to look at every mother and every father and should return back pretty much the entire tree. And in this case, well, let's take a look at the results. Okay, so we get everyone back here. The difference from just saying select star from this table originally is that if there was anybody in the table who was not directly linked as a parent, they would have been left out. But we get it in the order. So it starts out with William, Prince William. It has his parents, it has their parents, and so on. So the further down the list, it represents deeper in the family tree or further back in time. Oh, question came up? What's the question?
Yeah. I've seen CTEs which show missing dates, something like select blah union select blah +1 day. Is that considered a recursive CTE?
Okay, so the question was if you're doing a union all where you're adding a day into it and based off a specific date, you're adding one day at a time. Yes, that's considered a recursive CTE, and that's a great question because that leads us into an example we'll get to in a minute. So yes, definitely that is considered recursion. Okay, so let's take a look further here, because I think the interesting thing is, I mean, most of what we've seen so far, you could probably do pretty much with some filtering and stuff like that. But where it gets really interesting with recursive CTEs is how do you format them? How do you get really interesting data out of it? And honestly, when we look at this result set, that doesn't excite me as really interesting on the data output. And if you're going to try and display this in a family tree or something in your application, you've got a lot of work to do to figure out how to get that formatted correctly in some kind of a tree structure. Okay, so let's take a look at this. We're going to take a look at tree path. So we've got the same royal tree CTE here. We're going to add in a couple of things. First, we're going to add in level, which we've used in the past, which just shows us how deep in the hierarchy we are. We're going to start out with 0 as the initial level, and then on the recursive side, it's going to take whatever level the previous result gave and add 1 to it. That's kind of related to the date question we had a moment ago, but you can see that each level through the family tree, it's going to be able to update that person and show Prince William is at level 0, and then how many generations back before Prince William are they. And then the second piece we're going to do is this tree path, where we're going to say, let's take the name, and at level 0, the only person in the path is Prince William, and we're going to say, take the name, cast it as a varchar 4096, and we're going to alias it as tree path. Okay, so why do we have to cast it? Well, the way common table expressions work is that whatever the first result from an anchor query is returned, that's the data type that's assumed for everything that's going to go into that column. But as the tree path grows, what I'm going to do is start concatenating things and stretching out the amount of data in there. So the longest name in the anchor query is going to determine the size of that field, but by casting it to a varchar 4096, and in some cases you might have to do a varchar max or other things, but for now, I'm just going to do it varchar 4K, because it's big enough for whatever we're doing here, and that will make room for other things to be concatenated onto it down below. So then next, at the first level on the father's side, we just take level equals level plus 1, and we'll do the same thing on the mother's side, but we take the previous tree path, we add on this little arrow with pointing at father and then a colon, and then we'll concatenate on the father's name. And we have to cast that again as a varchar, because that will end up being whatever its maximum size is, and you get a type mismatch where it says you can't union these, because you have to have the same data type on the union there, or the same size. So the casting is just get them all big enough that they're going to match up, and then it's the same inner join on the recursive part that we saw before, and then the exact same thing on the mother's side. The only difference is we're joining on the mother's ID, and we're putting the word mother in there. Then what I'm going to do is just say where the level is less than 3, so only give me Prince William, his parents, and their parents, which would be level 1 and level 2, so the parents and grandparents, and then order by tree path. And since the tree path is going to be set up to have everyone's names in it, we're going to get it sorted in an interesting style here. So let's run it, stretch it out a little bit, and we can now see it starts with Prince William. Let me zoom this in a little bit here. It has, the next section is everyone on his father's side, then everyone on his mother's side. It lists his father, and then from his father's side, it lists his grandparents, and then on the bottom, it lists the father and mother, which is the grandparents on the mother's side. So you're able to see the tree path is generated with each of these pieces that make up a full path that shows the relationship from one person to another person there, very similar to a path on a hard drive or any other place you may end up with some kind of a hierarchical structure like that. Okay, but still, that's better than just the list for representing how people are related. And there might be some great cases where you want to be able to display this type of data, but I don't like it yet because it doesn't really visually show me how people are related. So what I'm going to do here is I'm going to change this up a little bit. I'm going to use the same tree path as before, and that doesn't change throughout here, but I'm going to add in a new column into the results set called relationship. And I'm just going to call it top for the anchor query, which is Prince William. I'm going to call it, just have it be father, and it's cast to varchar 10 because varchar 10 is certainly big enough to hold top, father, and mother, because that's all that's going to be in that column. And then for every one of them, you're going to be able to have a column that represents who's the father, who's the mother. And then it's going to, down below, use the replicate function. If you haven't seen the replicate function, it just takes a varchar string passed into it and replicates at a certain number of levels. So it will indent parents 1 level, it'll indent grandparents 2 levels, great-grandparents 3 levels. And then it'll show the relationship. So, and still ordering by tree path. So the order doesn't change, but visually how people are represented through the tree seems to have improved a little bit. We can zoom in here and see that from the top level, Prince William, his mother's down here and his father's right here. And then from his father's side of Charles, his father's listed here and his mother's there. I'm not really good at drawing here, but you can see you kind of end up with sort of a family tree hierarchy here as it gets built out, representing indentation, and it's a lot easier to see who's related to who in what way in this kind of a structure. All right, let's take a look. Yeah,
Steve,
question?
If you were doing recursion in code and had 2 sections like this,
Yep.
it looks like it's doing the same thing, right? It goes through and does the first one, then it hits the father section with the royal tree CTE again.
Yep.
And recurses, and it keeps going until that one runs out, and then it pops at one time and goes down to the first mother one, and then it kind of goes through that, and then hits the father ones, and then so it's like I don't know, the code we call like an infixed traversal or something, right, or whatever. But
Yep. So
it's just like code, kind of in that regard.
well, it's sort of like if you had a recursive function. So the question is, how does this relate to code? I think
Kind of,
to get a better understanding of it, rather than repeating all of that. If you had 2 recursive functions in your code that called each other back and forth, I mean, imagine how confusing that might be or messy it might be. And one of them is called recurse the father's side, and the other is called recurse mother's side. And then you establish your base, and then you call each one recursively. And then inside of each one, it calls the other one recursively for each level of parents there. That's effectively what we're doing here. But one of the things that you'll notice is that the way this gets run is the anchor query gets run first. And you might think that next it runs all of this first union, and then next it would run all of the second union. But it doesn't work that way. It sort of goes through and does all of the unions at one level, and then takes all of the results that haven't been processed yet, and then calls all of the other union alls at another level, and keeps doing that each level after level after level. So it's like having 2 different recursive functions that are calling each other in this sort of cross-twisted kind of way. I don't know a good way to describe what that would be called.
Depth cursor.
So what caused it to
It's
order like the results with the father, father, father indented, and then pop 1, mother, father, 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 pop 1.
okay, so let's go back to the results. The question was, what causes the order of indentation here? So the order, first off, is determined by the tree path. So we're not currently displaying the tree path, but the tree path would be William, Charles, Philip, Andreas. And what that means is that everyone who's an ancestor of Charles is going to be sorted before everyone who's an ancestor of Diana. Does that make sense? So that's how the sorting is determined. But that's a really good question on how sorting is done, because that leads us up to how do we sort it more like a real family tree, where you start out with an individual, and then above that is one side of the family, and below that is another. That's where it gets interesting. So what we're going to do is we're going to throw out the tree path. We're going to keep the relationship, but we're going to throw this thing in called sorter. And what we're going to do with the sorter is we're going to give everybody a value of A, B, or C. B means you're in the middle of the sort order. If you're given an A, that means you're on the father's side. So the father's side would appear on the top of it. If you're given a C, that means you're on the mother's side. So the mother's side would appear on the bottom. And then what it does as we run through it is it builds out and concatenates. So like the father's side of Prince William might be B-A-A-A-A-A, where the mother's side might be B-C-C-C-C for all the mothers out. And then each mother and father through the entire hierarchy gets an A, B, or a C. We can then concatenate B's onto the end of it just to sort of stretch it out for anyone who comes up short as being in the middle. And then we order by that sorter value. Okay, a little bit twisted, a little bit confusing there perhaps, but what it's going to do is order the entire recursive query, adding on at each level this sorter value. Okay, so, and we sorted by it. So you can see down here, the first B is just William, that's Prince William. And everybody in the list that's above him is on his father's side of the family. Everyone that's below him is on his mother's side of the family. And you can, for everyone at their specific level, any parent that's above them is, or any ancestor that's above them is on the father's side, and any ancestor that's below them is on the mother's side. But where that gets interesting is if we add in the replicate function to extend it out by level, doing the exact same sorting, we then end up with a better structure here. I'll zoom in it, where we've got the top level is Prince William, which links to his father, and then you can see his father there, and Prince William's mother, and the mother's father, and the mother's mother, and you can see how you end up with an actual family tree, if we draw all the lines, type structure here, looking more like what you might expect. So if you were going through to scan this and figure out how you're going to display this type of a thing in whatever application you're doing, this might be a much better piece to, better way to format it, depending on where you need to go with it. Does that answer the questions on sorting and whatnot there?
So it really is still set oriented fundamentally on each select, and then they're just ordered to make it how you want.
Yes. So the entire result set comes back with each select, all union together, and then the sorting is done afterwards, because the sorting is outside of the CTE down at the very bottom, and we can sort it however we want at that point. And in that example, if you wanted all the mother's side of the family to be ahead of the father's side, you would just have to swap this A with this C here in those two sections, and you'd end up with the opposite sort direction, or add a descending on the end here. Either way. Okay, so that's it on the family tree and the hierarchical structure there. So let's get into a little bit more interesting traditional type recursive functions. So Fibonacci sequence, I don't know, did we cover Fibonacci when we hit the CTEs before briefly? So we'll just do a quick review of that. You build the anchor query, which is where recursion starts. And you can see the anchor query we get. Fibonacci sequence, for those who don't know, is defined as 0 and 1, and then each subsequent number is the sum of the previous two. So then what we're going to do is take 0 and 1, union all. We're going to just, in this case, let me zoom in on this one. Oops. In the Fibonacci, we have previous n and n. And what we're going to do on each one is we're going to select n, which will become the next previous n. And then we're going to take previous n plus 1 plus n. So it's adding the previous two numbers together all the way through, and it's going to do it out while n is less than 100 million. When we run this, you can see with the Fibonacci sequence, we then go out quite a ways, and it only gets 45 lines back to be able to calculate that out. So that's the quick review on Fibonacci. There's some other things that we can end up doing with the Fibonacci sequence to be able to display it in a line. And here's one of the things that I occasionally like to do is to use the XML path, which we'll cover that a little bit later in other sessions. But basically, we're going to take this entire result set, we're going to cast it out as XML, but the variables between them, we're not going to have an XML node. That's what this piece says, XML element. And then we're going to chop off the first XML and the last XML element, but each item has had a comma appended to it. So it's going to take our entire result set, which was a big column, and almost like a pivot it into a single string as our result set. And we run that, you can see there's our Fibonacci sequence calculated out here as a single result. Just a side trick there, that a way to take a big recursive result and convert it into a single varchar item. All right, so next on to factorials. We didn't hit factorial before, I don't think, did we? No, so that's a new one. With the Factorial CTE, factorial is represented as a number with an exclamation point off above it or after it. And what that means is it takes that number and multiplies it by all numbers down to including 1. So 5 factorial is equivalent of 5 times 4 times 3 times 2 times 1, which effectively comes out to be 120. 6 factorial would basically be 120 times 6 to get that number. So we'll start out with our anchor query, select 1, 1. Well, 1 factorial is 1, because 1 times, well, nothing is just 1 in that case. And then what we're going to do using the union all, here's where it gets recursive, is we're going to add 1 to the number, and then we're going to take that number with the 1 added to it and multiply it times the previous factorial, and that's selected out of the factorial CTE, so that's where it's going recursive, where the n is less than 5. I know we're doing a lot here on the recursion, but this is this kind of stuff will come up that you really need to know it for getting through the exam. So here you can see 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. Okay, well, we got the results there pretty quickly with a not that big of a recursive query. But what if we want to go further? 5 factorial, most of us probably could have done that in our head. So let's go with the factorial CTE and try going out to where n is less than 20. So let's go 20 factorial. Anybody know that one off the top of their head? All right, so, whoops, invalid.
Select more. And this is the top row.
Oh, whoops. All right, that's the error I was expecting. So arithmetic overflow, converting expression to data type int. Well, what happened at this point was 12 factorial fit into an integer, 13 factorial excluded what would actually fit in an integer. So remember earlier I said when you go recursive, when we're looking at the strings, the varchars, the size or the data type that's being used in the output column is whatever comes out of that beginning anchor query. So in that beginning anchor query, it assumed an int, because that's what SQL Server defaults to if you don't specify, and everything else had to fit in an int. But we wanted to do factorial of 20, which doesn't fit in an integer. So how do we fix that? Well, all we have to do in this case is cast the first one as a big int, and it allows us to go further all the way down to 20 factorial. And you can see there, you get a pretty darn big number there. It's one of these mathematic progressions that grows like crazy. All right, so that's cool. We got a pretty big number there. We've gone recursively to 20 levels deep, and we've been able to build out a really big factorial. Okay, what if we change this to 21? 21 factorial now blows up with type big int. It just doesn't fit. So what do we use? We take a look at numeric. So numeric is a data type in SQL Server that will give us 38 digits of precision. That's more than what you can get with an integer. But it's not enough to go forever. But let's take a look at this. So now we're going to go to 33. Here's our result set. Make it a little bit wider. Scroll down here. And you get a pretty darn big number for 33 factorial. Okay, well, that's our recursive query. Being a math geek and whatnot, I really want to go beyond 33 because you always have to push the limits, right? So let's go to 34. What happens then? Oh dear. We've overflowed the numeric data type. What do we do next? Maybe it's not something we should be doing in the
Big
data.
numbers in code.
Yeah. Big numbers in code would represent that kind of thing. Maybe it's not the kind of thing you should be doing in the database because, well, SQL Server does not have a data type that would represent bigger than this. Maybe you can come up with something nasty where you store it in a varchar and then you convert it out as a big num and do some math somewhere along the way. But no, this is as far as you can go with the numeric data type. So with this recursive CTE calculating factorial, we've maxed out SQL Server's data type for storing numbers pretty darn quickly.
I think Douglas Crawford created a 64-bit integer type that might be over him.
But it's not, that's in code.
Big int, right?
Yeah, yeah.
And there's actually one that's available in code that's even larger than that, that'll hold any number size. But SQL Server doesn't have those built into the T-SQL code. So that's why I said maybe we need to move it out of code at that point. Now, most of the stuff you want to do recursively, you could do in here, but that's just an example of sort of maxing it out and the kind of things you run into when you do some wacky recursion. All right, so let's take a look at working with strings. That's one of the things I mentioned we're going to do. All right. So we're going to create a function here that's going to split a string. And you come across this quite often. I know some of the when you try and do a lot of string processing or working with CSVs or other type of structures in the database that have a lot of text in them, you want to be able to chop them up somehow and parse through them in some way. So in this example, we've got a function called split. I probably should have called it split varchar, split string, or something like that. But we're going to use split. It's going to be splitting on a separator character that's passed through, which is just a single character. And you're going to pass in a string that's going to be split up, which is just a varchar 8000 in this case. You probably could have done varchar max if you wanted. And then it's going to use a CTE here to select, and using the char index function, which says, give me, it's like index of. It says, give me the first position of a given character in a string. So the anchor query says, give me that first position, and let's set the last position as 0, assuming that you're going from the very beginning of the string up to the first occurrence of it. That's your first chunk. I used the term chunk in here a few times, so I don't know a better way to say it. But the second one, we're going to start at the previous position plus 1 and search, and then use the previous position as the last position, and keep recursing until pause returns 0, or until that broken character or the separator character does not occur in the string. So what that's going to do is it's going to go recursively and tell us the position of each of these breaking characters throughout the entire string. And then outside of the CTE, it's going to break that string up based off of a substring of the last position, and then the last position plus 1, so skipping over the first occurrence, or skipping over the character itself. And then if the position equals 0, then just go to the end of the string, go beyond the end of the string. So give me from where I'm at to the end. Else it's the position minus the last position of 1, or else it's the exact length of the chunk you want to bring back. And so let's create this function. We could have done it outside of a function, but I want to be able to reuse it. And then what we're going to do is take the quick brown dog jumps over the lazy fox and select star from calling that function with the splitting character being a space. And notice here, I'm going to put the option max recursion outside here. So you can't put the option max recursion inside of the CTE, inside of the function. It has to go on the outside because it affects the entire statement that's being run. So when we run this, you can now see kind of the opposite of what we did with the XML trick earlier. We took a string and broke it out into chunks, and we can see the quick brown dog jumps over the lazy fox, almost like pivoting a string on a specific character. And I use pivoting kind of loose there. It's not quite the right term for it, but it gives you the idea. So here's the starting paragraph starting paragraph on a chapter I was writing a couple years ago. And I'm just going to put that paragraph into this variable called input string. I'm going to rip through it and pull out all the punctuation, all the carriage return line feeds, and any duplicate spaces. So by the time all these replaces occur, it's going to end up with just words and spaces, no periods, commas, anything like that. And then what I'm going to do is I'm going to call the split function with that input string. So when we run this, the paragraph is anyone can perform a SQL Server upgrade. SQL Server upgrade. And when we run it, you can see anyone can perform a SQL Server upgrade. Commas have been removed and all of that. Okay, well, why would this be useful? Well, if you needed to pull things back at a certain position in a string based off of a breaking character, you could then just go to the specific row to get the result sets. But what I'm going to do here is I'm going to call that split function. I'm going to group by the chunk, which is each individual word in this case. I'm going to order by the number of usages, which is just a count, and it's going to give me a word count of the entire word count for all the words used in that paragraph. Oops, I forgot I have to go all the way back up and select the input string here. Ignore the first one because we already looked at that. We're looking at the second here. And you can see the word the is used 18 times. The word to and of are used 8 times. And then a, SQL, server, that, and a few others here are all used 6 times. So if you were writing code to do like a tag cloud or something like that on a page or a blog entry or something like that, you could come up with what the most commonly used words are out of any chunk of text pretty darn quick with this. All right, so that's an example of how we can split it up and then group and do something with the results. Next, I'm going to create a new function called split with line number. Same parameters. Actually, I didn't really do clean code here, but S refers to this, the input string. And it's going to be calculating the positions the same as we did before, but I'm going to be casting them as big ints just so that if we've got a really long string, we can handle it. But then I'm also going to come back with a line number. So as it's creating each row, it's generating a line number. So it tells you how far or how, basically the same result we saw a moment ago, but with a line number attached to each one. And then we select the same substring as before, and we throw that into a function. All right. So same thing we looked at with split, but you get a line number on it. Next, I'm going to create a second function called varchar diff, which you pass it in two strings, S1 and S2. You then select from split with line number on string 1, left join it to split with line number on string 2, where the line numbers match, and then it's going to give me, based off of matching up of the line numbers, all of the items where the left chunk does not match the right chunk. So all of the lines that don't match. Now, this is just playing around with recursion here. It doesn't do very good if there's new lines inserted with a specific function, but it'll tell you what lines are different. So if you look at this paragraph here, it's the same one we had before. Anyone can perform a SQL Server upgrade, going on through it. And then we have a second one, input string 2, which is almost the same as before, but there's a few differences in there. And I'm assuming that nobody looking at this string can point out exactly where the differences are. But if I select star from the varchar diff function, passing in those two strings, I can now see, oops, oh, I forgot to, there we go, I forgot to create that. So we get the two strings, we call the function, and we can now see of those strings, there are, or of that entire paragraph, or those paragraphs based off of line feeds, I guess it's more than paragraphs, there's a couple of differences. And we can see, assuming it's not the right thing, what you will need to know versus what you need to know, minimal downtime versus minimalistic downtime, and the resource or budget that you have available versus the resource or budget that you have. So very quickly, it's found 3 lines that are different out of those 2 paragraphs. I've used this in the past when we were doing test cases built into the database where we were looking at one set of code that was supposed to generate some output string, and then a way to be able to test and say, does the output string really look the same? And if it doesn't, show me where it doesn't match. All right, that's it on the strings. Now on to dates. The question was, earlier I heard, can we have a recursive query where we're working with dates, where we start out with a given date, and then we add 1 to it. So what I'm going to do here is I'm going to start out, and I wrote this query a couple years ago, with 2013, January 1st as the anchor query. If we run that, all it'll return back is just January 1st, 2013. We're then going to use the date add function to add 1 to it, and then we're going to call that calendar date, and we're going to go recursively and keep doing this recursively as long as the date add is less than January 1st of the next year. We're going to select star out of that, and let's highlight this and run it. And I've purposely left out this max recursion at the bottom here. When we run that, we overflow max recursion because 100 is the default, but we've got 365 days or 364 depending on a leap year. So I've just set max recursion to 366 just to be safe. We run that, we now get a list of all of the dates in a year. Now back to what I mentioned earlier, imagine if you're a doctor and you're trying to schedule a golf trip around those dates that you do or don't have appointments at your clinic. Well, you could use this list and then do a left join with exclusions up to your list of actual appointment dates, and then give a list back where all of them are null on one side, and you'd be able to see all of the dates that you could go golfing. All right, so another thing we can do, because that just gives us the dates of the year, we can use these date part functions down here for year, date name, month, date part, day, date name, and all these things to do a similar query, but come up with different pieces of the calendar. So if we're looking like at what weekday, we could extract all the weekdays out of a list that way, or the day of the week, or the day of the month, things like that. Useful to use when you're trying to work through a list of data to find missing data or holes. All right, so next we're on to the numbers CTE. Now, one of those things you've probably seen if you've been around enough databases is you'll have a database where somebody creates a numbers table. And a numbers table simply contains numbers. And you use it for doing joins, do exclusions, and things like this. But oftentimes when people look at that, you think, okay, well, I'll create a table, and I might have a primary key, or I might do some other stuff around it that has some other data in it with my numbers table, and it can end up being pretty darn big. And then you think, okay, well, I built this numbers table that I want to use in my database, but I don't ever want to have it fail on me, so how many numbers do I have to put in it? So, I mean, the obvious answer I've seen done in a few cases is they say, okay, well, it's a numbers table based off of integers. Let's just put in the max int number of numbers. And you end up with this really big table that's used to do things like calculate what day of the month is, are we missing data on, or something like that. So you can look at that and say, okay, well, do we really need the max int size of data to calculate days of the month? And last time I checked, days of the month are either 28, 29, 30, or 31. We don't need much larger numbers than that. So we can do things with a CTE to simulate what people have used a numbers table before. And here I'm going to call it with numbers CTE. We're going to look at our anchor query, select one. Okay, pretty darn easy. That's where we start. Our numbers table can start at 1. If we wanted to start at something else, we could start it somewhere else instead of 1. And then all it's going to do is just add 1 to it. And it's going to select 1 plus the number from the numbers CTE, and that's where it's going recursive, where the number is less than 1,000. And then outside of the CTE, it's just going to say, give me all the numbers. And with the max recursion being 1,000. Okay, so we run that. We now get the numbers 1 through 1,000. Probably a lot cleaner on your system than building out a numbers table that has max int number of numbers in it. But let's take a look then at some other ways of using this. So what I'm going to do is I'm going to create a table called people. Every person gets an ID, they get a name, and they get an age. Okay, the table's created. And what we've got here is I went and just queried on the most popular 40 male and female baby names recently, and then I threw in ages on all of them. So if I highlight this entire thing here and ask anyone, tell me what age is not represented by this set. Well, that's kind of hard to do. You have to scan through it, and some of it falls off the screen. Good luck finding what age between 1 and 50 is not shown in the list. So let's just fill up the table. There's 80 rows there. Half male, half female, with just a bunch of random numbers I typed in for dates. And if we select star from people and say, okay, tell me what's missing. Well, it's not in any specific order, so good luck trying to figure out what's missing. You could probably have some kind of a checklist you go through and calculate that out. But what if I just order by age? Okay, so we can order by age, no recursion, nothing like that here. And we can scan through it and say, okay, 1, 2, 2, 3, 4, 4, 5, 6, 7, 9. Oh, there's an 8 missing. All right, we got one of them. And keep going through all the way through that, and you could find all of them that are missing. But this is a really small data set. What if there were 100 million rows in this data set? You'd never get through that to figure out what was missing. Okay, so next, let's trim it down a little bit. Let's just look at the distinct ages. And now we get fewer results, and it's quicker to scan through because I can see that 8 is missing, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18's missing, and then some other ones are missing as we go through there. But still, you don't want to have to write code that involves you visually going through and checking a result set. So let's take a look at how we can go through and write a query that will just give me back all of the missing ages. So here we've got the exact same number CTE we looked at a moment ago, except for instead of going to 1,000, I'm only going to 50 because that's the ages we're looking at. And actually, technically, I'm only going to 49 because I'm going where the number is less than 50. And selecting from the CTE, I'm going to left join it up to people. And again, the left join says give me all of the numbers out of the CTE and match it up with the people if there happens to be a match. But if there's not a match, leave it as null. And then I'm going to join it on the age of the people matches the number in the CTE. We can then run that. Okay, as we go through the list, we've now got everyone out of it matched up on the CTE number, and anywhere that there's not an age, it's shown with nulls. So you can quickly scan through here and say, okay, there's nulls. Oh, 35 through 42, there's nobody in that age range. But if we want to filter it out, all we have to do is say where the p.age is null, meaning where there's no people with a given age that matches the numbers in the numbers CTE. You can then see, okay, here are the ages that are, there are 14 ages in that range of 1 to 50 that are not represented. Okay, so let's clean up the output a little bit, because I don't need all the nulls there. So all I'm going to do is just change it to say, give me the age, and we're going to alias it as missing ages. Cleaner list here, same numbers. But what if we want to make that query a little bit cleaner? Because honestly, this is a little bit larger than what you need to do if you're generally using a numbers table. However, with most number scenarios where you're using a small set of numbers, it's much more efficient. Now, if you're working and generally looking at how do I find out what integer values are missing, you might want to have a numbers table. But in this case, with smaller values, anything less than a few thousand or even tens of thousand is going to perform quite well. But let's clean it up a little bit more. So what I'm going to do is I'm going to take that numbers CTE, throw it into a function, and I'm going to call it numbers, create the function, and select star from the function to give me numbers 1 through 50. There's our numbers. A little bit cleaner than doing the whole CTE if it's something you're going to commonly use. And then my query with the left join to figure out all the ages that are missing gets cleaned up to look about like this. It doesn't look recursive because it's simply a left join. However, it's calling a function that goes recursive and generates out 50 numbers. And you can see that query returns the same 14 missing ages that we looked at previously. All right, that's it on recursion for today. Keep in mind, it's a great way to do all these things shown here. Hierarchical data, things with tree paths, recursive mathematical calculations, string parsing, finding holes, finding what's missing. And at this point, any questions? We'll pause here for a minute and see, let the video catch up and see if anyone has any questions. In the meantime, anybody in the room have any questions for anything related to merge or data recursion?
Since the CTEs are processed every time they're run,
Yep.
it seems like there could be quite a bit of additional CPU load on the server if you're having to generate that, especially since it's having to do recursive calls. And
You would think that, but if you look at, I mean, CTEs are truly amazing on how efficient they are in doing those recursive calls. And it depends what you're doing. If you're simply adding one or adding a date to something and you want to do a list of 0 to 30 or 0 to even 365 for a whole year, CTEs are so darn fast, so much faster than being able to even access a table in memory. So if you're pulling them out of a table, it's going to be slower to go through the data pages and pull all of that data out of the table into your query than it is to do it recursively with a CTE. However, recursive CTEs get ugly and slow and messy when you get into tens of thousands or millions of levels of recursion. So as long as you're not going millions of levels deep or even hundreds of thousands of levels deep with recursion, it is just the fastest way to do it.
even if it's called often.
Yeah, even if it gets called often.
Okay.
And especially if it's called often for calculating 1 through 30 or 31 for days in a month, it's so fast to calculate that, even if it's called often. And again, I didn't repeat the question, but I'll repeat the next one if there's any other questions. Any other questions?
In the that last function we were looking at, is the parameter used
This one here?
that max number?
Oh, so the question was, is the parameter used in here? No, good catch. So it was a copy and paste mistake from before. It should have been worded in. And is,
Somebody might find, or you might use that.
yeah,
in a different number.
good catch. So if I just do an alter table or alter function using that max number parameter, run it and change this to give me through 50 and another one that says give me through just 5, and then run both of them. One result set, yep, goes all the way through 50, and the next one just gives me 1 through 5. All right, good catch. I don't know how many times I've used that demo and nobody's got that before, so thanks for catching that. Any other questions? Are we caught up yet on the questions over here?
Yeah, we're on this.
All right. Well, that wraps it up then. A couple more notes here. For more information, you can visit emergencyreporting.com to learn more about the company, or you can find Aaron or me on the web. Aaron's at aaronbuma.com or on Twitter as Aaron D. Buma. And I'm on the web at stevestedman.com or SQL EMT. Tune in next week. For those who've been following along in the book, we've hit the end of book 2 in the series. So next week, we're going to do a review. What I'm going to look at is a review or sort of lightning talks. We're going to try and spend about 5 minutes on each of the topics. Then if anybody has questions on anything we've covered so far, we can explore those questions at that point, and just do a quick summary review of everything we've done. And then we'll come back and do another review of that in the very end before you guys get around to taking the exam. But I just want to make sure that for anyone who came in late or anyone who might have missed a presentation, we'll get at least a quick touch on everything that we've gone through. Plus, if anyone's behind on the reading, it's a great time to get caught up on the reading. All right, that wraps it up. Thanks everyone for attending.